SwayamPrabha. Digital India. Educated India.
So, last time we considered Zhukovsky's transformation for two specific cases, if I remember correctly. One in which the center was placed at the origin and that parameter in the Zhukovsky's transformation B was taken equal to R, which resulted in a flat plate airfoil. We considered another case where again we placed the center of the circle at the origin. However, that two critical points z equal to plus minus b, they were kept inside the circle, that is b was taken as less than r, and we found an ellipse whose fineness ratio was determined by the relative magnitude of b and r. We will consider few more cases as specific examples, and the first one that we will consider today is that the center is now shifted from the origin along the the imaginary axis. That is, center is no longer at the origin, but it is shifted along the imaginary axis. Let us take that circle plane or zeta plane. The center is not at the origin, but somewhere here. Okay. This is the center. However, we make such that the two critical points z equal to plus minus b, they lie on the circle. That is, this is what is b, and we call this length say m. So, the center is at and if we remember the definition of the angle beta, this is the angle beta, then what will be m in terms of beta? M equal to r sin beta and B or R and B, they are also related. B sec beta. Okay. One thing is clear, that since both the critical points are here lying on the surface of the circle, after transformation both will become two sharp corner. This point as well as this point, they will become sharp corner, or the resulting geometry will have two sharp corners. Now, let us say what is this transformed geometry? What is the transformed geometry? Put these in the transformation z equal to zeta plus b square by zeta. Any point on the circle will be given by f 0 plus r e to the power I theta. Substitute that in the transformation, then what will be the points on the surface of the transformed geometry, x and y. Zeta equal to zeta naught plus r e to the power I theta. Okay. So, zeta naught is I m, zeta naught is I m plus r e to the power I theta. Substitute this in the expression z equal to zeta plus b square by zeta. R, of course, we have already seen, R is or r square equal to b square plus m square. Substitute this and simplify, what we will get is x equal to r cos theta into 1 plus if you look to these expression, particularly for that y coordinate, you will see that y coordinate will retrace the values for whatever we have for 0 to pi, then pi to 2 pi it will retrace the same values. And the resulting geometry will be this curve. If you look to it, this will be the maximum ordinate, we will call it maximum thickness, though it is of course not thickness, but we will call it thickness, and you can see that this will be 2 m. See, these two critical points on the circle plane, let us denote them by A and D. These are the two critical points. These two points transform to the corresponding points here as B, and this corresponds to say E. A is the trailing edge point, and we have earlier seen how to find the velocity at the trailing edge point on the transformed plane. On this plane, of course, the A is a stagnation point, and if the velocity is to be finite here, which must be, then this also must be a stagnation point in the circle plane. Remember that at the critical point, that derivative is 0. So, if the velocity is to be finite, then the velocity on the circle plane must be 0. That is the way we found what is the velocity at the point B. The same thing applies here now also at D and E. D is also a critical point. So, dz df or dz d zeta at D equal to 0. So, the velocity on the circle at point D must be 0. So, that we have a finite velocity here. So, this must be a stagnation point, and what is the location of this point? on the circle plane, the forward stagnation point. If you remember, we did it for the flat plate airfoil. For the flat plate airfoil, where was the forward stagnation point? We located the forward stagnation point for the flat plate when the flow was at an angle of attack alpha. We located that the forward stagnation point must be at pi plus 2 alpha. For the flat plate airfoil case, we located that the forward stagnation point must be at pi plus 2 alpha. So, in this case, where it would be? Pi plus 2 alpha plus beta. You can check it, you can write the complete complex velocity for on the circle plane in this case, and then see that this is what it will be. Of course, in this case we have used that similarity with the flat plate. In the flat plate case there was no beta. So, all the geometric points are shifting by beta. So, that beta is added to pi plus 2 alpha and the corresponding point on the circular arc airfoil you can find by transformation. What is the transformed coordinate of this point? The point which was pi plus 2 alpha plus beta in the circle plane, where it will transform after the transformation by z equal to zeta plus b square by zeta. That will give the forward stagnation point. Some straightforward result. What will be the chord of this airfoil, this circular arc? Remember, the chord is this length, this is the length of the chord. How much this will be? Assuming beta very small, approximate it, approximate the chord. Consider one point first, consider the trailing edge point. Which was at theta equal to minus beta. And take beta very small. This is what you will find. For very small beta. What is the velocity at the trailing edge? If you remember, z trailing edge equal to approximately 2b. For this we have already a general formula. This we derived earlier, q infinity cos beta, then cos alpha plus beta. What is the lift coefficient? The lift coefficient, if you remember, 8 pi r by c, is not it? 8 pi r by c sin alpha plus beta by sin beta, is not it? The relation. This also we derived earlier, 8 pi r by c sin alpha plus beta by sin beta or cos beta, sorry, not sin beta, cos beta. So, that r by c is 1 by 4. So, 8 pi r by c, that gives 2 pi. So, it becomes 2 pi sin alpha plus beta by cos beta, which is again approximately 2 pi into alpha plus beta for small alpha, and if alpha and beta are very small, this can be approximated to 2 pi alpha plus beta. If you compare it with the flat plate case, for the flat plate it was 2 pi alpha, for the flat plate it was 2 pi alpha. So, we see that it has changed here by 2 pi alpha plus beta, that alpha has been modified by alpha plus beta. However, the slope of the lift curve do not change. dCl d alpha is called the slope of the lift curve, that has not changed, it remains 2 pi. What we see that for a flat plate, Cl is 0 when alpha is 0, and which is quite obvious. If alpha is not 0, flow is along the plate. So, there will be no asymmetry between upper and lower surface of the plate, and hence there will be no lift. Here we see that the lift becomes 0 when alpha is minus beta. The value at which the angle of attack at which lift becomes 0 is usually called the 0 lift angle of attack. So, in this case the 0 lift angle of attack is minus beta approximately. So, this has changed the 0 lift angle of attack, nothing else. Or rather, if we plot the Cl alpha curve, we can see that Cl alpha for flat plate Cl alpha for flat plate is straight like this. Remember, these alpha and beta are obviously to be taken in radian, 2 pi alpha, alpha is not in degree, because you have made sin alpha plus beta is approximately alpha plus beta, that holds only if alpha and beta are in radian. So, this is for and what happened for the other case, the two lines are simply parallel. this alpha 0 is called 0 lift angle of attack. The angle of attack at which lift is 0. For a flat plate, this alpha 0 is 0 itself. For this cambered airfoil, it has become minus, for the circular arc airfoil it has become minus beta. Now, in terms of the airfoil or that is circular arc, what is beta? For the circle, okay, beta is the location of the that where you have placed the critical point. But in the if we talk it in terms of the circular arc airfoil, what is beta? See, beta is related to that maximum ordinate. And how much is beta? Let's see what is beta. Beta is actually nearly approximately tan beta, that is what? What is tan beta? M by B, and what is B? B is in terms of there is no R, for an airfoil there is no R, that R is only for our numerical help. So, after we get it, then we must forget about R and all those things, they do not concern us. It is C by 4. Then okay, or tell us in terms of Y max only. This is half of Y max. M by B, B is C by 4, B is C by 4, and what is M? Half of Y max. So, substitute all those. What happened? Half of Y max divided by C by 4. So, how much is this? 2 into y max by c. Now, this circular arc, we can also thought of it simply the representation of the camber line of an airfoil. It is the representation of the camber line of a cambered airfoil. And in that case, what is the y max by c? It is what is we call the maximum camber or called so much of camber, usually expressed in percentage. So, this beta is then so that is what is the implication of the beta camber ratio, maximum camber ratio. Okay. Usually an airfoil is designated by the maximum camber ratio, not the entire camber distribution. And what do you see what the camber does? Camber, from here we can see the camber shifts the zero lift angle of attack. Camber changes the zero lift angle of attack. If your airfoil has positive camber, then the zero lift angle of attack will become somewhat negative, approximately 2 times the value. So, if your airfoil has of say maximum of 5% camber, usually it will be called that airfoil with 5% camber. That implies that the maximum camber of the airfoil is 5% of the chord. Okay. Then this gives beta is approximately how much? 2 times of that, about 0.1 radian. So, an airfoil with 5% of camber will have a zero lift angle of attack nearly at minus 0.1 radian. How does it help? It helps because it allows you a wider range of angle of attack and wider range of angle of attack. We see that here the CL alpha curve is linear. CL versus alpha, which is called CL alpha curve, is usually linear, but this linear behavior comes because of our linearization of the equation. We consider our flow to be linear, Laplace equation. In real case, of course, it is not, but when the angle of attack is very small, it behaves almost linear, but as alpha starts increasing, the flow behavior becomes little nonlinear, and after some time, instead of increasing lift, the lift will start decreasing. Usually it happens for almost all these airfoils somewhere in the range of say about 15 degree. For a finite wing it is little less also. So, the maximum angle of attack that you can use during flight is something, if there are no camber, is something between 0 to 10 degree or so. That is the angle of attack that you can use, 0 to 10. If you apply camber and say that zero lift angle become minus some 3 degree or 5 degree or so, then you can use the angle of attack from minus 5 to 10, you are getting a wider range. And at a particular alpha, you see that angle of attack the lift coefficient has increased. An airfoil which has no camber will give this much of lift at a particular value of alpha, while at the same value of alpha a cambered airfoil will give higher values of lift. So, at a fixed angle of attack, camber increases the lift coefficient, and in the general case you get a wider range of angle of attack to use. To complete, you can put this is the complex velocity on the airfoil plane, that is on the circular arc, and you can extract the real and imaginary component u and v and find the velocity on the circular arc. It can be done straightway. I am not doing it. The expressions will be quite lengthy, but it is quite simple to do. You can find what is w zeta velocity on the circle, that is known, we have already written down that expression. You substitute that dz by d zeta and carry out the operation of complex division and extract the real and complex. But once you find the velocity on the surface of the circular arc, the u and v component, you can find the pressure coefficient simply by 1 minus u square plus v square by q infinity square. Now, let us consider another case. In the last case, we shifted the origin along the imaginary axis. Now, we will shift it along the real axis. We will shift it along the real axis. And we keep one critical point, we take care so that one critical point is on the circle. The other inside the circle. That is, let us say this let us say we shift it by a very small magnitude, a very small amount from the origin. This is the origin, we place the center of the circle somewhere, say here, okay. Call the center of the circle O. We put the center here and then take one of the critical point on the circle. Oh, I think I should have taken it to this side. I think let's change it. Actually, this should have come to this side. We want to make it say B, but minus B will be somewhere here. This center sorry zeta 0, which will be taking okay. So, that zeta trailing edge, that is coordinate of the trailing edge is r e to the power I beta minus We will see what is this geometry. At this stage we have just considered a geometry like this, that okay, that this is the geometry which has been transformed to this. Now, what is this airfoil? I mean, whatever the geometry is, what it is surface. What is zeta? Zeta naught plus r e to the power I theta. Zeta is zeta naught plus r e to the power I theta, that is in general. Simplify and you will find that the transform geometry is given by x equal to r cos theta minus b epsilon one plus these expressions are of course not very convenient to handle with, but you can see that if you assume epsilon to be very small, then they can be approximated to we already had a relationship between r and b, if you remember from here, that this relation where it can be written as 0 or r equal to b into 1 plus epsilon. If you look to this relation for z, you can see that from here, agreed.